This lesson deals with MOSFET characteristics. You can find these notes in the ECE302 ebook in Chapter 4 starting on page 9. MOSFET is an acronym for a metal oxide semiconductor field effect transistor. There are two types of MOSFETs. One's called a depletion MOSFET and the other is called an enhancement MOSFET. They no longer make the depletion MOSFETs, so we're just going to talk about the enhancement type MOSFETs. And of those enhancement type MOSFETs, there are two, an N channel and a P channel. What's shown here is the physical structure of an N-channel enhancement type MOSFET. Starts out with a piece of silicon that's doped P-type, and then a section here and a section here is doped N-type. Metal is added over this N section and this N-type section, and they'll become the source and the drain of our transistor. Also, the substrate has a metal attached to it, and that'll be known as what's called the bulk. Between the drain and the source, there's also metal deposited with a layer of insulation underneath it. There's no physical connection between the metal and the P-type substrate. That's going to be called the gate. Because of this insulating material, there's a very high resistance between the gate and the source and the gate and the drain. The gate also has a width and a length, and this controls some of the parameters of the transistor. The symbol for the MOSFET has four terminals: the drain, the source, and the gate, but also the bulk pin. Between the bulk and the drain and the bulk and the source, look back over here, here's the drain and the source, and here's the bulk. There's a P-N junction. From the bulk is P and the drain and source is N. So you see an arrow pointing from the P material to the N material. The dashed line is shown here because there's no physical connection between the gate and the substrate itself. Current coming in here for DC is 0 because there is no physical connection. The currents are defined coming in the drain, going out the source, and coming in the gate. Now since the gate current is 0, the drain current will equal the source current. We can also have a voltage between the gate and source and the drain and source, but also voltages between the bulk and source and the bulk and drain. The diode that's between the bulk and source and bulk and drain has a VI characteristic with a forward drop. But we're not going to operate it here. We're going to operate it where it's either negative or just slightly positive. And if you do that, you then get a family of curves. Starts out and levels out. And as the gate source begins to decrease, the current begins to decrease. And eventually the current will go to 0. And that particular voltage is called the threshold voltage. We'll have three regions again. We'll call this the ohmic region, where it looks like a straight line, pretty much like a resistor. And then a saturation region, where the current saturates. And then a cutoff region, where the current's equal to 0. Let's apply some voltages to our N-channel MOSFET. I'm going to ground the source and ground the bulk, and then hook up a voltage between the gate and the source, and a voltage between the drain and the source. Let's take a look at the ohmic region where VDS is very small, say maybe 1/10 of a volt. And I'll pick the gate source voltage to be, say, 6 volts. So between here and here, I've got 6 volts. There's a P-N junction here and here. This node voltage is 0 and this node voltage is 0.1. The voltage between here and here is a minus 0.1. And so it's reverse biased. We have a depletion region between the P and the N material. The voltage between the gate and drain is going to be this node voltage of 6 minus 0.1. So the voltage between here and here is 5.9. The voltage between the gate and the source and the gate and the drain are about the same. The plus sign here is like a big magnet. It's going to repel positive charges. Now there's a metal layer here and then there's an oxide layer, which is just a high resistance material, but this is strong enough of a magnet that it repels the positive charge. And it creates a channel that has less positive charge in it. In other words, more N-type. We call this an induced N channel. This minus terminal repels an electron here. It has a place to go because the plus terminal is trying to attract it. We're going to repel an electron, attract it, bring it back around, and so on. We're going to have a current flowing in the opposite direction. What would happen if I were to make this voltage smaller? Suppose it was 5 volts. And that would make this 5 volts. This would be 4.9. Still have a reverse biasing, so I have a depletion region. But now my induced channel is not going to be as deep because I don't have as big a magnet here. It's going to be harder for an electron to flow and come back again, so the resistance is going to go up. Suppose I were to decrease this some more to the point where we don't induce a channel, say 3 volts. This would become 2.9 if this was 3 volts here. There's a point to where this isn't big enough to induce a channel, and I have no current flowing because I can't push that electron because of all the P charge that's here. If we're in the ohmic region, the gate to source and the gate to drain are both greater than or equal to threshold. When we're in the cutoff region, the gate to source and the gate to drain are less than or equal to threshold, and that causes the channel not to be induced into the block current. This is the case we were looking at, where we had 6 volts and 5 volts and eventually down to 3 volts. Let's next take a look at the saturation region. Suppose I make the gate source voltage again 6 volts, but now I come way out into the saturation region, say maybe this is 5 volts, and then that would make the gate source voltage here 6, but now the gate to drain would be equal to 6 minus 5, or 1 volt. Voltage across this PN junction here, and it's going to be 0 minus 5. We again are reverse bias, so we're creating a depletion region. But now, between the gate and the source, I have a big enough of a magnet that I can induce a channel. But between the gate and the drain, I don't have enough voltage to induce the channel, so I have a region depleted of charge. Well, the minus terminal here wants to give, again, the electrons in here a push, and the plus terminal wants to attract them. That push, if it's strong enough, like a bowling ball, can have it roll across here and get to the other side. Just like the BJT, just like the JFET, we have a region where we've got charge able to flow and then a blocking, and we're going to use the force of this magnet to give it a hard enough shove. There's only so many electrons here. If we can collect all of them, we get a constant current. When we're operating in saturation, the gate to source is greater than or equal to threshold, and the gate to drain is less than or equal to threshold. And this is described in the words below. And these are MOSFET characteristics.